Hey guys, welcome to Deep Dive Coding. Today we solve LeetCode problem of the day, and this is a medium problem tagged by LeetCode. So problem is balance a binary search tree. Previous day problem was binary tree and today's is binary search tree. So in this video I will explain the optimal and the simplest approach. So this will be the flow of the video. First of all, I will explain the questions, then simulate the test case, intuitions, build the algorithm, code explanations, and finally complexity analysis. I will tag these are in the chapters so you can skip in particular portions. So without further delay, let's start the video. So we given a questions that is given a root of the binary search tree, and we have to convert. This is given like this is a binary search tree, and task is to convert the height balanced binary search tree. In the previous video I have already explained the what is mean by height balance, so you can check that also, but I will explain over here also. Like if you for any node, if you try to calculate its height and it have some left child height and right, like left subtree height and right subtree height, and if you subtract that those left subtree and right subtree height, if the absolute value is less than or equal to 1, that is acceptable, that means this is balanced, otherwise it is not balanced. So if you check this node, that is 1, if you try to calculate this node height, this will be 1 2 3. So in the right child right subtree height, this is the right subtree height, it will give you the answers as 3. But if you try to calculate the left subtree height, this will be the null, so it will return the 0 over here. So if you take the difference of these two, it will give you the 3, which is less than 1. No, it's not. So it is not the balanced subtree, like balanced binary search tree. So if you try to do the balancing, you let's try to calculate for this node. So if you calculate for this node, left subtree height will be 2 and right subtree height will be the 1, and if you try to subtract and take the absolute value, that is 2 minus 1, and is it less than or equal to 1? Yes, it is. So it is a balanced, it is a balanced binary search tree. So another property of the main property of the binary search tree is simple, like we are given a root node over here, and if it is have the right child or may and also the left child, if the left child is exist, then let's denote that this is r value and this is l value, and again you consider this is rg value, so it is given as root value. So this will be the structure. So left child value will be less than root value and less than right child value. That means if you do this way, like let's take an example. So you let's root value is 5 and left child value is 3. This is acceptable because 3 is less than 5 and right child value should be greater than 5. That means you consider, let's say, 7. So yeah, it's binary search tree. Now come into the test case simulation part. So we have to convert it as balanced binary search tree. So is this tree balanced? No, I already given the explanations. Now try to balance this subtree. So if you try to fix these two as the root node, let's try to take as root node, then we can, what we can do, so 1 will be placed left child and 3 will be placed right child, and also 4 will be placed right child of 3. Is it balanced for this one? So left subtree height is 1 and right subtree height is 2. So is it balanced? Yes, it is balanced. Another balance also possible. Let's try to for 3 as the root node. So if 3 is the root node, then to place 2, where to place 2? It will be the left child because lesser than 3. So it will be left child, and let's try to place the 1 also. It will be the left child of 2. And if you try to place the 4, it will be the right child of 3. So now let's left subtree height is 2 and right subtree height is 1. So is it balanced? Yes, it is balanced because 2 minus 1 taking absolute value, it will give you the 1. Is it lesser than or equal to 1? It is. So it is balanced binary search tree. Now coming to this part, this is the second example. So is it balanced? Let's try to first, is it binary search tree? Yes, it is, because 1 over here, 1 less than 2 and less than 3, it is balanced binary search tree. No, sorry, it is binary search tree. But is it balanced? Yes, because left subtree height is 1 and right subtree height is also 1. So if you take the absolute value of these two things, it will give you the less than equal to 1. Yes, it is. So it is balanced. I think you got the questions correctly. Now try for the intuition part. So if you observe these things closely, like at finally, to calculate the answer, tree should be the binary search tree. So when we try to do balancing, we cannot violate these conditions. At the end of the result, it should be a binary search tree. Like for end result also, it will hold all the conditions which is apply for binary search tree. Now for the second thing is, at the same time it should be balanced. Now if we give this an node value, let's try to build a binary search tree. How you can do the balancing part? So let's start, there are 7 value given. So to balancing it out, so let's try for this value 4 as the root node. So now let's try to do this part and this part. So this part will go to the left child and this part will go to the right, like this part will be go to the left subtree and this part will go for right subtree. Why? Because all the left subtree should the value less than 4 and all the right subtree value should be greater than 4. That means you can try to compute for this part only. So it will be, let's take a middle value, it will be like 2. Now when you place the 2, now you have two options, like for 1 will go to the left subtree and for 3 it will go to the right subtree of 2. That means 1 over here and 3 over here. Now for similarly this part will be calculated 5, 6, 7. So it will go to the right subtree of 4. Now let's place the 6 over here, that will be the middle value, and 5 will be left subtree and 7 will be right subtree. Now if you calculate the height of the left subtree of 4, it will give you the 2, and if you calculate the right subtree of 4, it will again give you 2. So 2 minus 2, taking mod, it will less than equal to 1. Yes, it is. So it is balanced. So if you closely look into these things, like if we have the value in the sorted format, so we can pick the middle value as the root node, and for left part will be go to the left subtree and right part will go to the right subtree. In this way, if we recursively apply these same operations, then it will be obviously always balanced. So now the problem is, we want node values in sorted order. How we can do these things? One thing, we can traverse all the nodes and place in the vector and try to call the function sort. Another thing is, we can use the property of the binary search tree, as I already mentioned in the previously. So property is left child values less than root value and right child values be greater than the root value. What it mean? In let's what we can do in the in order traversal, first we traverse the all the left node, then right node, and then explore the root node, and then explore the right node. So in this order, also the binary search tree conditions is left value is less than root and less than the right value. So if we traverse in the in order traversals and place and pushing the all the values in the vector, then that will be the in the sorted format. So we just, instead of calling the sort for n log n function, n log n, it takes big of n log n time complexity, but we do not need it, because we just traverse in order. And when we do this in order traversals, when we call, let's in order, first we try to in order left node, like we try to explore the left subtree, then we just push back in a vector, let's name as nodes, and just push back the node value, and then try to explore for the right subtree. So this will give you the sorted vector, like nodes will be the sorted at last. Now let's come into the algorithm part. So first of all, we need to traverse in order traversal for all nodes in sorted way, and second thing is recursively construct the balanced binary search tree. As I already mentioned, first we select the middle element as the root node for each subsequent problems, and build the left subtree will be the left half, and build the right subtree of the right half, and at last we just return new roots of the balanced binary search tree. So now let's come into the coding part. So first of all, here it is the starting point. Also I am showing this code in C++, but you can find Java and Python code exactly similar. I will attach these things in the descriptions. So first of all, tree node balance BST, it is given as, so it will take the root node, like root node is given as an argument. So first of all, we takes the vector of nodes to store all the nodes value in like sorted format. Now first step is in order traversal to insert all the nodes in the nodes vector, and second step is we just build the binary search tree, and we passing over here L, that is low where to start and where to end, that is 0 to node dot size -1, and passing these nodes for the building part, and this will these functions will return the tree node root, and we just return that things. So let's come into this in order first. In order traversals to collect the BST elements in sorted order, that means we take the root and have the nodes also passing as reference to store it, like update in the functions also. Now if the root is null, then we do not need to do anything. That means we already in these positions. Let's consider this is the 4 only elements, and its left child is null and right child also null. When we try to explore this null, we do not need to do anything, just to return it. So because we do not like process this null element. Now try to explore for the left subtree by using root left pointer, and when we processing the roots, we just push back the node value, root value you can consider, and at last we just process the root right, that means right subtree. When this in order call is done recursively, we have the in the nodes array we all the nodes in the sorted format. Now when we try to build this binary search tree, we take few arguments. First of all, left where to start, right where to end, and takes the nodes value. And if this is the invalid conditions, if the left greater than right, that means we are in the invalid conditions, we just return null, because we do not need to insert any elements over here. And if it is valid conditions, that means left less than or equal to right, that you can consider this way, that first of all we try to calculate middle element by left plus right by 2, and second we just initialized a new node for the root node, that you can consider new node equal to new tree node of nodes of mid by considering this. That means let's consider an example. So 1 2 3 is the nodes value, so and 0 1 2, and let's consider left over here at 0th positions and right over second positions. So it will give you the mid as left, that will 0, plus right, that will 2, and divide by 2, so it will give you 1. That means this will be the middle node, this is middle pointer. Now when we try to calculate we initialized a new node, so you consider 2 is the value of the new node, you consider this way, new node, this is the new node, and which left is still null and right child is also null, but we assign left and right by recursively. And now recursively build left and right subtree. For root node left, new node left, it will give you the bind. Again we call the same functions and passing this variable, that is left to mid minus 1. That means these portions only for the left subtree part, and for the right subtree part we place the middle plus 1 comma right, that means this part only. So in recursively it will place 1 over here and 3 over here for this example, and at last we just return that particular root node. So in this way we can solve this problem efficiently. Now let's come into the complexity part. So if you look into these things, like first of all in the main functions we just first call the in order function. So in order functions will iterate each node once, so it will be big O of n if n equal to number of nodes, n equal to number of nodes. Now for build the BST we again traversing each node at once, so it will again give you the big O of n time complexity, so you can consider it as big O of n time complexity. And for the space we store node value, so it will take big O of n to store all the node values. And for the recursion stack space, if it is queue format, then it will take height, or you consider as big O of n as well, so you can consider space complexity goes as max as big O of n. So yeah, thank you guys, thank you for watching. Stay tuned for more videos, and I will upload the notes in the descriptions and also attach the LeetCode solutions in the video. And please subscribe the channel and if you like it. Thank you guys.